Good morning or good afternoon, ladies and gentlemen. Thank you very much for inviting me to this conference. Thank you for the opportunity for me, Sarinova Simandjuntak, and my colleague Bin Lin to share our work on combining residual stresses and fluid structure interaction finite element analysis for induction bending pipes integrity assessment at elevated temperature. I must say that most of the modeling work was done by my colleague Ping Lin. We are from the University of Portsmouth in the UK, from the School of Mechanical and Design Engineering. And this is my email address for future correspondence or for any questions following this presentation. I will follow this outline of presentation. I will start by mentioning our motivations, why we conducted this work. So we are looking for an effective methodology, more towards modeling approach methodology that can correctly capture the stress distribution in the pipe. And this is to enable us to predict or assess life of structural components more accurately. We have created a series of finite element models to simulate the pipe geometries, the bending, residual stresses, and fluid structure interaction in the pipe. All are using Abacus software. To verify our finite element models, we use published data. For example, data published by Kajespur and Yetisir, who conducted experimentation and finite element modeling of a cold bending process of a pipe to determine stress or residual stress distribution along the bend pipe. We will also analyze the influence of pipe bending and the von Mises stress distribution, particularly at the elbow areas, at the intrados, extrados locations, where sometimes we see a big variations in the geometry, such as the thickness, thus affects the stress levels in those areas. We would like to think that at the end of the work, we would be able to propose a stress analysis method of the steam pipeline components. We will start our work by develop a bend pipe model and then run simulations of the residual stress only model, followed by a different simulation. So no connection here, a fluid structure interaction model using CFD methods. And from each of these steps, we will generate stress and temperature fields results, which are subsequently becoming our initial conditions for the final simulations. And the final simulation will implement residual stress combined with fluid structure interaction models to simulate at elevated temperature around 323 degrees Celsius. For the pipe materials, we are referring to A106 grade C or seamless steel pipe materials, which is a good materials for high temperature application. For our model, we are referring to the ASME standard material stress and strain curve here for the A106 grade C. But for the validations purposes, we are taking the stress and strain curve profile from the Kajespur and Yetisir published data. And this one in particularly was obtained from the area or locations denoted as U575. So this is not a material, it's just a denotation for a location along the bend pipe reported in Kajespur and Yetisir publications. The results or the readings of the properties are more and less similar or in agreement. There are some more informations on the material properties listed in this table, as well as the dimension of the pipe for our models. We are also referring to the temperature-dependent material properties of the A106 grade C, such as the elastic modulus, yield stress, conductivity, specific heat, and thermal expansion. They are all as a function of temperature. So the first step of our work is to perform pipe bending modeling, where the cold bending process of a pipe was modeled using Abaqus explicit version 6.14-1. We introduced some parameters, some context, such as the context between pipe and clamp, pressure, die, and roll, with a friction coefficient of 8, 0.1, and 0.4 respectively. We use C3D8 continuum elements and R3D4 rigid elements of Abaqus to model the pipe and the clamping beam respectively. Meanwhile, the R3D4 elements were also used in the modeling of the clamp die and pressure die. We conducted a mesh convergence analysis where we found a good convergence for the pipe at a maximum element of 0.06 millimeter. We also connected the clamp to the roll using Abaqus beam connector to allow movement with the roll around the same center. And then we applied rotation on the roll at origin of coordinate 0 during the simulation of pipe bending process. This figure 3 may be able to help expressing all those conditions and constraints mentioned before. Once we've done the model, we run the simulations, and our results from the simulations were compared with the measurements results from the experimentations done by Kajespur and Yetisir. In short, we found that they are pretty much in agreement, so the simulation and the measurement results are pretty much in agreement. So this gives us a confidence to move to the next stage or step, which is the fluid structure interaction modeling. For this, we are using the model shown in figure 8. First of all, we will remove all the contact pairs from the pipe. And we applied some viscous pressure parameters on the pipe to reach a quasi-static equilibrium quickly. We can introduce or we use Abaqus explicit setting option to import the coefficient of viscous pressure Cn into a viscous pressure loading. But we would like to make sure that Cn is kept to a small value to minimize ongoing dynamic effects. For the thermomechanical analysis, we can refer to this figure 8b on the constraint that was introduced. So we are looking at the distance at length equals to 45 times diameter. And this is to eliminate the elbow effects on fluid velocity profile. We also introduced a film coefficient and sink temperature at the internal and external surface of the pipe during the heat transfer analysis. We make assumption that the fluid is incompressible and Newtonian, as well as has no slip or no penetration conditions on the wall. So we run the FSI simulations and the result are verified again using the published data. This time is reference 3. The details of these references are in the final slides of this presentation. So what we are trying to show here are the profile of velocity against locations, and the locations are along this diameter of the cross-section of the pipe. And this is referred to the distance with regards or with respect to the diameter. So this is 1 times diameter, 10 times diameter, 40 times diameter distance from the elbow. Again, it shows that our fluid model are more and less in agreement with the reference data published in the journal. So using the stress fields and the temperature fields and use them to or for our initial conditions in the finite element model, the thermomechanical finite element models, which can be applied through user subroutine dilute. And also we activated the Abacus power law creep model during the analysis using these parameters, again, to allow us comparing for like with like. So for these are the parameters for the materials and the conditions that we are simulating. And all these are considered or used in the final simulations using the combined residual stress and FSI model. We have the results of stress distributions along the bend pipe at room temperature as well as at elevated temperature. I think this slide will show a bit more clearer details or results. We extracted these stresses from the area in the elbow of the bend pipe, at the extrados, intrados, and flank areas of the bend pipe. And we can see that for the residual stress only finite element analysis at room temperature, it shows a very high stresses or stress levels compared to the stress levels obtained from the thermomechanical finite element analysis at room temperature. The elevated temperature models shows a reductions in the stress levels for both cases. And it seems that the creep model applied to the residual stress only finite element analysis reduce quite a lot of stress levels, and this is thought to be a result of stress relaxation. We can also obtain the equivalent plastic strains, which is very useful for the either fatigue or creep life assessment. So in conclusion, the finite element models that we are proposing can simulate the pipe bending and fluid structure interaction at the pipe elbow. And we can, at the moment, verify these models with the published data. Of course, we are planning to validate our models with experimental test data, our own experimental test data in the near future. From the high temperature combined residual stress and fluid structure interaction simulation, as you can see from previous slides, von Mises stresses and equivalent plastic strain on the bend pipe relevant locations are reduced in comparison to the stresses and strains obtained from the residual stress only model. And the power law creep model for elevated temperature pipe bending simulation resulted in much reduced stress value. So to end my presentation, here are the references details, and I would like to say thank you for your attention. I'm ready for any questions you have. Thank you.